in the textbook, probability distributions. First of all, you're going to see some frequency tables such as this. So random variables and probability. If you have a variable that is usually a value, hopefully numerical outcome, and it changes for every event, so that's called a random variable. It's usually a countable number. That means it is a discrete random variable, such as this one right here, which is, in a toothpick box. If there's supposed to be 250 toothpicks, there's a good chance there won't be exactly 250 toothpicks. So it's right here. They say the number of toothpicks varies from 248 to 252. 50 boxes are taken off the shelf, so the total is 50 here. And it says the number are counted, the results are shown. Find the probability that a randomly chosen box has 250 toothpicks. Well, there are 22 boxes out of the 50, so 22 out of 50 is, 11 out of 25, which is going to be 44%. All right, find the probability that a randomly chosen box has at most 250. So when you say at most, that means it's including anything at 250 and those less. So we're going to add those three up. 22 plus 13 would be 35, and 5 more would be 40 over 50, or 80% chance that it will have at most 250 toothpicks. Okay, so that's just finding probability from that table. You can also take this table and find the probability of each item happening, and like they did down here. So probability distributions, in order to show a probability distribution, you have to have every possible outcome so that your probabilities equal 1. Your probability is obviously always greater than or equal to 0 and less than or equal to 1. So it has to be between 0 and 100%. And then when you add them all together, it has to be 1, because if you're doing it as a decimal, that would mean, so 0.21 is the same as 21%, or 0.05 is 5%. So these have to add up to 1, which is, in a sense, 100%. So when they ask you to show that the distribution is valid, what you're going to show is that when you add them up, so 0.21 plus 0.05 plus 0.30 plus 0.17 plus 0.27, if you're going to show that that will add up to 1.0, and then all values are greater than or equal to 0 and less than or equal to 1. They're all within that. So that's how we know that this is valid. All right, so what are we even keeping track of? What's this? Motor vehicle production in the year 2000. So the U.S. produced 20.21, Canada 0.05, Europe 0.3, Japan 0.17, and other 0.27. So if a motor vehicle is chosen at random, what's the probability that it is made in a country other than the United States? A couple different ways you could do this. You could add up all of them except for the U.S., or, as I like to cheat, I like to go 1 minus 0.21 would give me 0.79, or 79%. All right, and then make a probability histogram. That just means every category goes over here, and then your probability is going to go up to where it belongs. So the U.S. is 0.121, so about right there. A Canada is 0.05, so there. Europe, 0.3, all the way to the top. Japan is 0.17, and other 0.27. And there you have it. There's the histogram. You want to color that in so it looks pretty? You're more than welcome to. All right, pretty simple so far. How do you show that it's valid? Add it up equal to 1. Show that all the values are between 0 and 1. And there you go. But here's where I thought it gets a little bit tricky. The expected value of a discrete random sample is a weighted average of the variable. All right, so it tells you what average the expected value tells you what average value to expect after a certain number of trials. So here's what you see. Let me show you how that's done. So you have to find the probability for each one. So here, a school is holding a raffle to raise money. The potential prizes and the probability of winning each prize are shown in the table. So if the prize value is $5, you got 1 in 50 chance. If it's $25, you have a 1 in 250. So those are our probabilities. I'm going to change the 1 in 50 into decimals. So this is 0.02. 1 in 200 is 0.005. This is 0.001, and this is going to be 0.0005. Those are our probability of winning. So we're going to take each value of the prize times the probability and add them all together. So a $5 prize, oops. Oh shoot, here we go. So a $5 prize is 0.02. A $25 prize, 0.005. A $50 prize, 0.001. A $75 prize is 0.0005. So why is the extra one there? The extra one is there because if you don't win the 5 or the 25 or the 50 or the 75, which is pretty likely, you're going to win nothing. Who's left to win nothing? And where do we get that from? Well, you add all these up and subtract it from 1. So 0.02 plus 0.005 plus 0.001 plus 0.0005. Add them all up and subtract it from 1. So it is 0.9735. So 97% chance you're going to win nada. So we created our probability distribution. Done. It's right there. Now calculate the expected value. Here's when I'm going to take 5 times 0.02. I'm going to add that to 25 times 0.005. So I take the value of each prize times the probability of actually collecting that prize. So 50 times 0.001. I'm running out of room. 75 times 0.0005. And the last one we almost don't have to do because 0 times 0.9735, that's going to be 0. So we've got this one is 0.1, this one is 0.125, this one is 0.05, and 0.0375, and that one would be 0. Add them all together, and our value is, now that is a dollar value. What that means is every ticket purchased can be expected to win 31 cents. Because it's a 2, I'm going to leave it at 31. So every ticket purchased can be expected to win 31 cents. Now, obviously, it doesn't make a lot of sense because none of the tickets are going to win 31 cents. There's some winning 5, 25, 50, and $75, but on average, the expected value, it's a weighted average. So I would say that you use this value to determine what you're going to sell every ticket for. So on average, if they're going to pay out 0.31 on every ticket, then you're going to be selling more than that. You want to be selling each ticket for more than that price so you can make something on it. All right, so you have your worksheet. Come and talk to me. I do know that the first one is a little bit tricky with the blues and the yellows, so if you need clarification on that, feel free to come talk to me, but otherwise you should be able to follow this and be fine. Good luck. Happy end of the textbook.